explain or discuss about the acidity or basicity of this molecule. Actually, these molecules or these hydrides are made of these 2p block elements. So, as we know, going left in the periodic table to right, the electronegativity increases. If the electronegativity increases, it will result into more covalent character. It is true. So, if we consider hydrides from this lithium to fluoride, it is expected that the covalent character will increase. So, from that logic, we can consider that okay, it's ionic and it is covalent. It is also true, but not that much simple what we are thinking. Why? Because last time I have explained another factor, that is the bond polarity. Which is generated due to electronegativity difference, and this bond polarity introduces reactivity in the molecule. Actually, we are not discussing only the element lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. We are discussing about their complex. So this general statement will be modified little bit. So right now we have to explain the acidity of the material in this series. For example, this is not acidic, this is basic. This is, you can also consider basic. This, from that point of view, we can't explain properly. Actually, they are not basic. I'll explain it later. This is very less acidic. This is neutral in nature. Actually, this is little basic in nature. This is neutral in nature. This is acidic in nature. These three compounds we have explained in the previous video. Why I stopped here? Because I can't say they are not acid from the point of view H plus donation, but they are Lewis acidic in nature, which I will explain. This Lewis acidity, Bronsted acidity, all these things later. But one thing as information I am saying that these materials are Lewis acidic in nature. For example, if you go to lithium, beryllium to boron, the Lewis acidity factor is increases. So up to this we understood that this side is acidic, this side is non-acidic. Okay, and basicity, from here to here, if we come up to this, means ammonia, we can see that basicity increases. This methane is a neutral molecule. I will explain or make a separate video on this methane. So I guess in a crude way I have explained these details. You will understand slowly. After making many videos, I will explain one by one. So second, we are going to explain the properties of water. Why? Because water is a very important molecule, and we have observed that biological system is working in water as a solvent, and water is considered as an amphiphilic solvent because it has the capability to dissolve organic, inorganic, different types of solute. It acts as a solvent and it is capable to dissolve different solids. So let's discuss about water and its property. Water is made of 2 hydrogen atom, 1 oxygen atom, and more precisely if we say this oxygen has lone pair. The central oxygen is sp. Bond angle is around 104 to 5 degree centigrade, in between 104 and 105. These hydrogens these hydrogens are little delta positive character and this oxygen is delta negative character. I have explained this in my last video. This is happened due to the difference in electronegativity, which introduces bond polarity, and this bond polarity, because of the higher electronegativity of oxygen, which is around 3.5 in Pauling scale, and hydrogen is around 2.2 in Pauling scale. So this became delta negative and this hydrogen became delta positive. So up to this we understood the polarity of water, and now we are going to check or explain how the polarity of water affects its capability as a solvent. As a solvent means it will dissolve many solids. So let's take the simple example, sodium chloride. Sodium chloride gets solubilized in water as sodium hexaaqua complex and chlorine hexaaqua complex plus and Cl H2O 6 minus. How? Actually sodium chloride is, we are writing in this way, actually it is an ionic compound. Ionic compound means it remains as sodium plus and chloride minus. See, water has little excess of negative charge, that is delta negative, this oxygen moiety, and this proton has little excess of positive charge or little deficient of negative charge. So this is delta positive, this is delta negative. So we can say this oxygen, this delta negative can react with this sodium plus, because this negative charge will try to stabilize the plus charge to some extent. Similarly, this positive charge will try to stabilize this negative charge. And how this stabilization happened? Let's explain. And actually this stabilization is called the solvation, because when we pour sodium chloride into water, it gets solvated. For example, previously it has an ionic bond, stable, and after the solvation, first this ionic character broken and it became solvated. In my last video I have explained that every molecule wants stability. So this is happening spontaneously, that means it has some stability. Okay, let's explain. Sodium, it coordinates with 6 water molecule directly to form this hexaaqua complex, and this hexaaqua complex formation is the main reason for solvation of sodium chloride, and this formation releases energy such that sodium chloride to sodium chloride complex overall process has a negative delta G, means energy releases. That's why this process goes on spontaneously. Okay, so this is the process of solvation of sodium. Similarly, chlorine is solvated by this hydrogen of water molecule. Okay, we have explained the solvation of inorganic salt. Let's take an example of acid or bases. Let's take example of acid, HCl, and another base or alkali, that is sodium hydroxide. Why I have taken this example? I could have been taken potassium hydroxide, I could have been taken hydrogen bromide. No, I have taken this hydrogen chloride and sodium because it will help you to correlate with this theory. How? Let's see. For example, this HCl, it has a chloride common part. So stabilization of chloride you can check from here. How proton will be stabilized? Proton will be similarly stabilized by like sodium plus. Right? Sodium is also monocationic species. This is also monocationic species. So this can also be stabilized by the lone pair oxygen of water molecule. Similarly, so this is stabilized. Let's take sodium hydroxide. We have already observed how sodium is getting stabilized by water. So this part we have already explained. So the next term is hydroxide. Like we have seen previously, chloride forms hydrogen bond. Chloride form hydrogen bond. So after hydrogen bond formation, it getting stabilized. So similarly, like chloride, this can also capable to form hydrogen bond with the hydrogen of water molecule. Additionally, this can participate also hydrogen bond formation in with water molecule. So that's an additional stability factor. So what we have understood, that acids or bases getting solubilized in water by these interactions. So we have checked. Okay, we have already only explained about the inorganic materials, but water is called an amphiphilic solvent. So everything is soluble, means every type of material gets soluble in water. So let's take an organic material. So since we have discussed about ionic or more polar bond, so let's first take a more polar bond which ionizes easily. For example, acetic acid. What happens in presence of water? It forms acetate anion. Actually, it hydrolyzes to give proton and acetate anion. This is stabilized by water. I have explained previously. This is also stabilized by water. Actually, this all stabilized by water, and additionally, this remains in a resonance form. I have given the negative charge here. Actually, we can draw another resonance form of this, and actually these are the two canonical forms, but the molecule remains. The electronic distribution will be like that. That means the negative charge is distributed over two oxygens equally, as these resonance structures are equivalent canonical forms. So in this way, acetic acid getting stabilized. So let's take about alcohol, because we know that alcohol is completely miscible with water. So let's take about the example of alcohol and see how alcohol is getting stabilized. Let's take ethyl alcohol, C2H5OH. See, like water, the polar protein molecule means this bond is polar, as well as this contains an hydrogen. So what happens? This hydrogen forms hydrogen bonding with the oxygen of water, oxygen lone pair, and this oxygen is capable to form hydrogen bonding with the hydrogen of water molecule. So in this way, ethanol is getting soluble in water. Okay. So what we understood, water has two types of polarity. One is positive side, that is the proton part, H hydrogen part, and it has also negative side, that is the oxygen part. So any type of reagent, if we provide which have negative hydrogen, that is hydride, that will react with water, because water has a delta positive character, so they will react. So this is the reason that hydride reagents react with water very efficiently. So up to this, we'll stop about discussion about the water here. Now we'll go to our next topic, that is the hydrides of lithium and beryllium. So lithium hydride and beryllium hydride. Lithium hydride is made of lithium and hydrogen. So let's take the preparation. Lithium hydride could directly be prepared from lithium plus hydrogen, but it requires little high temperature, which is around 600 degrees centigrade and require a very less amount of carbon as catalyst. Here we can see that one gas is reacting with one solid and the product is solid. Okay. So according to Le principle, if we increase the pressure of this gas, it is expected that it will convert into product easily or more efficiently, and that's exactly the same thing happens here. Increasing the hydrogen pressure requires less drastic condition and it reaches the complete conversion of lithium hydride early. The thing is that if you check the molecular weight of lithium hydride, it is around 8. Actually 7.9 something, it's 8. Actually lithium has around 6.9, hydrogen has 1, so 8. And it is ionic in nature. And this gives us this material as a unique tagline, that is lowest molecular weight ionic compound. Okay, lowest molecular weight ionic compound. And this ionic nature arises because lithium is in group 1 and its electronic configuration is 1s2 2s1. This is lithium's configuration. So its outermost valence shell contains 1 electron and hydrogen has only 1s1. And lithium has a tendency to donate its electron and became a lithium plus. Electronic configuration 1s2. And this electron is taken by the hydrogen to form hydrogen minus. In this way, the two atom hydrogen is getting also 1s2, lithium is also 1s2. So both are stabilized. Another point we need to discuss about the size of hydrogen versus hydride, since our whole discussion is based on hydrides. Actually, if we see the hydrogen atom, that is, this is the nucleus and 1 unit positive charge, and this is the electron cloud surrounding and it contains 1 electron. Okay, fine. Let's add 1 electron to form the hydride. What will happen? This is 1 unit positive charge, but here 2 unit negative charge outside. So let's consider it as the previous size. For example, this. Right now, what change happened? Here electron number increased, but in center no positive charge increased. So at another point we know that this electron remains outside of this nucleus because of Coulombic attraction force. And another thing, electron repel another electron due to repulsion force. So here attraction didn't increase but repulsion increased. What will happen? This charge will repel each other and the orbital size of that anion will increase. Means the effective area occupied by this electron cloud will increase. And that's why hydrogen is a very small molecule, but this hydride is a very big molecule because of this electron-electron repulsion. And it makes hydride as a reactive reagent also to give its electron to someone or react with someone who has deficiency of electron to produce some stable molecule. One of the example, let's take hydride minus or lithium hydride plus water. It will react to form lithium hydroxide plus hydrogen gas. And actually, if we explain it in more clear picture, we can understand that the reaction is happening between hydride and hydrogen. Hydride and proton, for example. This hydride comes from this lithium hydride and this proton part comes from water to form a stable hydrogen means a dihydrogen material. Here 2 electron, here no electron, and ultimately 2 electrons shared by 2 atoms to fill their outermost valence shell and they are stabilized. Okay, so let's discuss about beryllium. From left to right of periodic table, when we increase, the extent of ionic nature decreases. What does it mean? That it means that ionic nature decreases but the covalent nature increases. Why? Because for beryllium, outermost valence shell is 2s2, 2 electrons. So it is not that much easy for beryllium to give 2 electrons, because it will be more electron deficient compared to lithium, because lithium released 1 electron, it is releasing 2 electrons to form this beryllium hydride. Okay, let's come to the preparation of this material. This material could not be prepared like other alkaline earth metal by reacting that metal center plus hydrogen to form this dihydride. Only this beryllium do not participate in this type of reaction, but this material could be prepared from different way, that is beryllium, tertiary butyl beryllium. Heating this tertiary butyl beryllium will result into the formation of beryllium hydride, and this temperature required is around 200 degree to 110 degree centigrade. Additionally, it could be prepared from dimethyl beryllium plus lithium aluminium hydride, which will eventually produce beryllium hydride. Okay, so this is the preparation. Now its property. This material actually is a polymeric solid. Polymeric solid means this beryllium hydrogen will form bond with another beryllium to form this polymeric solid, and this bonding is called 3-center 2-electron bond, which I will explain in little details, because this is one of the unique property of this beryllium hydride material. (3C2E) bond. This is beryllium, this is hydrogen, this is hydrogen. Here if you count the outermost valence electron of this beryllium, here 2 and here 2, so total 4. But to stabilize it requires 8 electron. Right now it has 4 electron, so it needs electron. How it can have? Since this material do not have any other electron, so it forms another type of bonding with another beryllium to form this 3C2E bond. What happens? These 3 centers, center 1, center 2, center 3, this is 3 centers. 2 electron means this only 2 electron, here no electron is there. So what is happening, this 3 center is sharing these 2 electron, that's why this is called 3 center 2 electron. And this electron cloud is distributed over these 3 centers and it is getting stabilized. But if you ask me one question, that is, if we consider the stability of this bond, this beryllium hydrogen or this beryllium hydrogen with the bond of this water molecule, is it that much stable? The answer is no, because this pair is shared only over these 2 atoms. So each atom is getting its own required amount of electron, but here they are not getting. But when they did not have anything, means highly deficient, to counterbalance the deficiency, they are distributing electron. So they are somehow stable. We can consider in that way. This material is stabilized by this 3 center 2 electron bond, and this bonding result into a polymeric structure of beryllium hydride. So another one example, it's a very important type of bonding, that's why I am explaining. If such type of bonding is found in BeH2. I shall explain about BeH2 in my next video, and that's why it remains in dimeric form. What happens here? This boron, hydrogen, and these middle hydrogens, they are participated in 3 center 2 electron bond, because center is 3. Center 1, center 2, center 3, and electron is 2. So 3 center 2 electron bond. That is the reason that BeH2 remains in dimeric state. And there is one confusion. Actually, sometimes people make confusion with AlCl3. That is also in dimeric, but their bonding nature is different. And this may come a question that explain or discuss about the bonding nature of B2H6 and AlCl3, or like that, which one is 3 center 2 electron, which one is 3 center 4 electron. So that's why as a comparison I am explaining. That is 3 center 4 electron bond. This is 3C 2E. How? AlCl3 twice. What happened? This aluminium, Cl. We know chlorine has 3 lone pair, and 1 lone pair is donated to aluminium, here also 1. And we consider it as a 3C4E bond. But there may be a confusion. Here we have 2 electron 3 center, but here we can, instead of that we can say 1 to 3 center. Okay, fine. 2 to 4 to 6 to 8 electron, but that's not true, because 3 center 4 electron, this statement is given based on the bond involved here, the electron involved in the bonding. This lone pair and this lone pair is not involved in the bonding. Only this is involved in the bonding. That's why how many electrons are involved? 2 electron from here and 2 electron from here. So ultimately 2 plus 2 4 electron. That's why 4 electron, and 3 centers are 1, 2, 3. That's why 3 center 4 electron bond. So this is the end of my video, today's video. We will explain next day on about this BeH2 or boron hydride and its properties. So hope you guys have enjoyed this video. This is my beginning in YouTube. So any limitation or any improvement suggestion, please comment, and if you like my videos, please subscribe my channel and give a like button. So thank you everyone for listening my videos, and please subscribe my channel Chemistry, the Mystery of Molecules. Hope to see you soon. Take care.